Good morning, everyone. Okay, so just give me a couple of minutes, then we can start.
हेलो। हाँ बोलो। क्या कर रहे हैं? सब्जी काट रहे थे। तो मुझे कौन सी आवाज कैसे आ रही है? कहाँ बैठे हो? अंदर ही बैठे हैं।
Okay, we can start today's discussion. Uh, all right. So, good morning, everyone. Welcome to today's discussion. Today, we will talk about. Today, we will cover the content of week 9. So, in particular, we will study about inner product spaces, distances between two vectors in vector spaces E2 or R2. Okay. And why. So, before we jump into that, let us first understand why do we need distances. Okay, so we need distance, uh, notion of distance of any two vectors to approximate data, okay, or to fit a data into a straight line or into a well-known curve. So straight line is the simplest curve that you can think of. So you can have data like this. These are the data points, and you can fit these points into a straight line. Okay, that is what you want to. So you want to find out uh, the minimum distance between the points and the straight line. So that to fit uh, the data. So for that, you need the notion of distance. Okay, between two vectors. Okay, so today we are going to study that. So first, notion of inner product space or the dot product space, also known as the standard inner product in R2. So when you have two vectors in R2, you can express your vectors respect to some basis. You can write down their coordinates. So whenever the basis is not mentioned of the vector space R2 or C2, you can assume that they are canonical basis. All right. So suppose you have vectors expressed in terms of the canonical basis, and they have the coordinates x1 y1, and v has coordinate x2 y2. Okay. Then you can define the dot product of these two vectors as, so dot product of these two vectors is x1, x2. We multiply the first coordinates and then we sum it, we add the multiplication of the second coordinates. Okay, this is what the definition of the, this is the definition of the dot product. Okay, so let's take an example of this. So you have these two vectors 1 2 and 0 1. So what would be their dot product? In both of the cases you can answer.
So you have to tell the answer.
Yeah, you need to tell the answer. Yes.
So for the first one, it would be 2,
All right.
and second one 0.
Second one. Right. So this is how we define inner product spaces. This is how we define dot product. Similarly, you can define the dot product in vectors, for vectors in R2 or for vectors in C2. And how do we do that? For complex, and this is called a complex inner product or a standard inner product for complex uh, vector spaces. Okay. So again, you start with two vectors, uh, u and v, and suppose with respect to canonical basis, they have some coordinate representation. They have a coordinate representation given by u1, u2, and v1, v2. Okay, in C2. Then the way to define the dot product is u dot v is equal to u1 v1 bar plus u2 v2 bar. Now notice here that each of this ui or vi is a complex number in itself. Okay, and what is a complex number? So a complex number has two components in it. So a complex number z in C is basically a plus I b type. Okay, iota b type. So it has a real part and an imaginary part. Okay, which is multiplied by I. So each of ui is a number like this. Okay, each of ui is a number like this. Similarly, each of vi is also a number like this. So we define their dot product. So we define their dot product is equal to u1 times v1. So this is the complex multiplication. Okay, and then we add these two quantities together. Now multiplication of two complex number is a complex number. Okay, so this addition of two complex number will give you another complex number. Okay. So the dot product of two complex numbers, or dot product of two complex vectors gives you a complex number. So what you can think of it is it as that it is a function. This is a function. This u dot v. Let me write it like this. Uh, let's say dot c. Dot c is a function from C2 to C. Okay, so it takes two vector and then it gives you a complex number. Similarly, you can think of the inner product that I defined earlier as a function, let's say dot r from R2 to R. So it takes two vectors in R2 and then it gives you a real number. All right. So now you may ask, what is this u bar, vi bar? Okay. So this is called the conjugate of a complex number. So you guys have already seen this in the first lectures when we introduced the complex numbers. So this is a conjugate, so you can quickly recall. So for example, if your complex number is given by z is equal to a plus ib, then z bar, the conjugate of it, is nothing but a minus ib. Okay, this is a conjugate. So let's take an example of this question. So suppose u is equal to I comma minus I. Okay, and b is equal to 5i comma 2 plus 3i. So I minus I complex dot product is equal to this, is equal to I, and then vi. So this is my u1 u2, this is v1 v2. So ui times v1 bar. Okay, so what is b1? b1 is 5i, and what is b1 bar? It is minus
Minus
5i,
5i.
right? It is minus 5i plus u2, which is minus I, times v2 bar. So v2 bar is 2 minus 3. Now let's solve this. So it is minus 5 I square minus, so I will take this minus out, and then you will have 2i plus 3i square. Okay. Now what is this number? Is it is so
It
minus,
has plus could be minus 1, so it would be 5.
yeah, it is 5. So I square is minus 1, so it is 5. And last thing is I 3i square, that means minus 3. So 5 minus 3 minus 2i. Okay. So this is nothing but 2i, 2 minus 2i. Okay. So it is a complex number.
So can we use J instead of iota? Because of signals classes, I was doing this wrong in circular matrix also. I was writing this as J.
Uh, no, iota is the symbol, is the standard symbol.
Yes,
J
sir,
is
but
not.
in electrical we use J na, so that's why I was mixing both of them. And there was one formula where you wrote J as variable, but I took it as iota.
So what do you want me to do?
Can we also write this iota as J?
Then what? How will it help you? I don't get it.
Sir, it's just the habit. In the signals we write iota as J. That's why.
Signals you write iota as J, and okay, 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 okay. All right. But then it will be confusing for others. Like, I don't know. Let's just stick to this notation. And for math course, you can think that iota is the complex number variable. Okay. Because J, we do not use J unless yeah, J is not used. So iota is the standard notation. So, okay, even in the lectures also it is iota. So if I use J here and you go back to the lectures, it will be iota over there. So it will be confusing in this course. So it's better to have uh, they use the same notation which is used in the course lecture. Okay, because like in the exam we will be asking iota, so there won't be any J. So okay, so now let's do this example also. Okay, so this example, you have two vectors u and v. Okay, both of the vectors looks like they sit inside R2, but anything that is in R2 is also is also a vector in C2, so they also lie in C2. So now let's calculate their complex inner product. So u dot v is 1 comma 3, 2 comma 4. Now this is u1, this is u2, this is v1, this is v2. Now by definition it is 1 times b1 bar. Now what is b1 bar in this case?
2.
2. There is no imaginary number, so it is 2 only. Similarly, plus 3 times v2 bar, which is 4. Okay, so this is what? This is nothing but 40. Okay. So what we can say? So we can say that, so what you have noticed from this is that the complex inner product is if you apply complex inner product on vectors which is in the R2 subspace of C2, then okay, you can think of R2. So R2 is a subset of C2. That is clear, right? So R2 is a subset of C2, but it need not to, it is not a subspace. You need to be careful when you say subspace. So clearly R2 sits inside C2. Okay, any vector which is in R2 is also a vector in C2, because you can think of that imaginary part is 0 and then it sits inside that. So the inner product that you have defined, that you have used for C2, can be applied on R2. And when you restrict your inner product, which you define for C2, if you restrict that to R2, then it becomes the real inner product. Okay, that is what we have seen earlier. Okay, so this is one thing I want you to notice, that because since C2 is in R2, the complex inner product, the complex dot product restricted to R2 is the same as dot product in R2. Okay. Now let's see some of the properties of inner product in C2. So first property is conjugate symmetry. So what is conjugate symmetry? If you, because you have noticed that u dot b is a complex number, so u dot b is same as bar of b dot u. What does this mean? If you take u dot b and you change the order, okay, then you will get b dot u. Okay, but that b dot u is not equal to u dot b, but its conjugate is equal to u dot b. Okay, so let's take the same example that we took earlier, this example. Okay, so we have found out that u dot b was 2 minus 2 minus 2i. Now let's do v dot ui. So I am taking two vectors in C2, and now let's do v dot ui. So v v dot u, sorry, v dot u, not v dot ui. V dot u is first b v 5i. What is ui? U1 is minus I, because you need to take u1 bar. Okay. Plus v vi, which is 2 plus 3i, and then you need to take bar of minus I. Bar of minus I, that means conjugate of minus I is just I. So you will get minus 5i square plus 2i plus 3i square. And what is this value? This value is 2i 5 minus 3 plus 2i. So this 2 plus 2i. Okay. Now let's check what is b dot u, conjugate of this. The conjugate of this is 2 minus 2i. Now is it equal to u dot b? Yes, it is equal to u dot b. Okay. So this is equal to u dot b. So this is called conjugate symmetry. The symmetry is after taking conjugate. Okay. Now if I take, now instead of now let's check for the inner product for R2. Okay, so let's check for the inner product in R2. So what kind of symmetry do we have in that case? Because in R2 we don't have conjugate. Okay, so if I take two vectors for R2, so let's say U1 is 1 comma 2, V1 was 0 comma 1. Then we check that U dot V was 2. Now let's check V dot U. What is V dot U? V dot U is 0 and 2. So this implies that U dot V is equal to V dot U. So this is same. So real inner product has symmetry, whereas the complex inner product has conjugate symmetry. Okay. And the simple way to think about this is that the conjugate doesn't make sense. Conjugate of a real number is itself. So the conjugate does not change. So so that has to be just the same. Now let's. So the second property that this inner product is inner product has is the linearity in the first coordinate. So you can,
Excuse me.
yeah,
One question about how we are defining the complex inner product itself.
yeah,
Is there any reason we use the conjugate over there? I mean, we do U into V bar. Is there some reason for that?
yeah. The reason is basically there is a definition of inner product. Okay, so that the inner product definition, in order to satisfy the inner product definition, you need to have conjugate here. So what is the definition of inner product? That definition is precisely a function that satisfies these three properties. Okay, the property that I'm discussing. These property become the defining property. Okay, so that is why it's the basically what you are seeing is the reverse of what has been in reverse of the order in which the things were defined. Okay, so complex inner product was defined later, but before the definition of an inner product, and then you can generalize this to complex inner product.
So in short, these properties will these properties have to be satisfied, and for that we need to do the element of the first one normally and then multiply
Yes,
with
yes,
the
yes,
corresponding element conjugated
yes,
of the
yes,
next one.
yes,
Okay.
yes,
Okay, thank you.
yes. Right. So linearity in the first coordinate. Now, how to check this linearity? It is quite easy. What do we mean by linearity in the first coordinate? That if you have u1 plus z u2 type expression, which is then it linearly expand uh, with the dot product, behaves linearly. So it is easy to check. If you start with the LHS, that is u plus z u2 dot v, then it is nothing but u dot mm, yeah. So let's take u1 to be some u11 u12 and u2 to be some u21 u22 vector and v to be v1 v2 vector. Okay, and then you can do the rest of the computation and prove that the LHS is equal to. So what is the rest of the computation is, first you take u1 plus z u2, so that will give you u11 plus z times u21 comma u12 plus z times u22. Okay, and then you do the dot product, the complex dot product, and then you do the complex dot product. That means uh, this whole quantity, this z u21 u12 plus z u22 dot product with v1 v2, and then if you do that, by definition it will be u11 z u21 v1 bar plus u12 z u22 dot v2 bar, and
Sir,
then
there
again,
would plus in between ZU12 plus.
Right. There's a plus. And then U11 V bar plus U12 V bar. Okay, you club this together, and then the rest will be Z you can take out, and then it will be U1. Okay. Now this is the expression for U dot V, and the second is expression for U dot V. Okay. Sorry, U1 dot V and U2 dot V. This is the RSS. All right. So this is how you can prove that it is linear in the first coordinate. Now, using the first and the second property, the linearity and the conjugate symmetry, what we can show is that it is conjugate linear in the second coordinate. Okay. So that is what it is, conjugate linear in the second coordinate. That is what I'm writing over here. And what does this mean? That is, if you take this, so U dot V1 plus Z V2. Okay, so now this is equal to the conjugate symmetry. Using conjugate symmetry, you will get this is equal to V1 plus Z V2 whole bar, sorry, dot UV U whole bar. Okay, this is what you will get. Now, but conjugate of this whole expression. So, right, now let's just go back in the proof of this. Okay, so now you can have the conjugate property over here. So you can have, now you apply the conjugative property, the linearity property in the for this dot product. Okay, because you have this linearity in this dot product, so you apply that. So you will get V1 dot U plus Z V2 dot U. Okay, now you put it back in this. Now conjugate. Now this is the real number. So first, sorry, these are the complex numbers. So this is sum of two complex numbers. Okay, and conjugate distribute behaves well with the conjugate of two complex number. So you will get V1 dot U bar plus Z bar V2 dot U bar. Okay, now this is what? This is nothing but U dot V1 plus Z bar V2 U dot V2. Okay. This is this. So you will get this expression. So this is what called the conjugate linearity. So why conjugate? Because this expression is equal to this, but the only difference is that Z bar will come out instead of just Z. Okay. You can have this expression in generality also when you have some coefficient multiplied here as well. So let's take the general argument Z1 plus Z2. Okay, instead of just having Z in the second as this thing. So you can have Z1 plus Z2. So you will get something like Z2 bar and Z1 bar in front. So this is the general expression. Similarly for this also, I can write down, let me write down the general expression. Z1 and Z2. So you will have Z1 over here and Z2 over here. Let me box these things.
Excuse me.
Yeah.
The operation regarding Z, could you explain that again? We managed to pull Z bar out of the whole big Z V2 U whole bar. We managed to pull Z out of that. How did that happen, please?
We managed to pull Z bar.
I was thinking that when we conjugate this thing, line 3 over here, line 3 in this expression,
This
when we
one?
conjugate that one, so when we conjugate that thing, clearly v1 bar, I mean v1 dot u gets a
So
whole bar.
if you conjugate this,
Right, that one will break at the plus sign. That is clear.
yeah, right,
Both are complex numbers, so they will be
yeah,
individually conjugated. How do
right.
we pull z out of that product of three conjugates? I mean, the
No,
conjugate.
this is basically what this is z1 dot z2 bar is equal to z1 bar z2 bar, right?
Okay, this one I
This is
didn't.
the complex multiplication. This is complex
So
multiplication.
this holds true all the time.
This is a complex multiplication, right?
Okay, this one property I had forgotten. Okay, thank you.
Yeah, you can quickly check this property. X plus iy x plus I some a plus iy ib. So it is what is this? This is xa plus I this. No, no, it is I bx plus ay, and then minus will come here. It will be by. Right. Now let's do the conjugate one. So it is minus minus over here. So we'll get minus again here. This will be given as it is. And then there will be minus sign. So yeah, this is fine. Okay. So this breaks. Conjugate behaves well with the product and the addition. Okay. So
And
this
important
is,
thing is that ZV1 is not a inner product; it's a simple product.
yeah, this is complex because how it can be an product, because V1 is a vector and Z is a complex number. So it is a scalar multiplication,
Okay, okay,
right?
okay. So it's like that. Okay, thank you.
Yeah, these are the scalar multiplication. So it is where these are vectors in C2, but Zi's are in C, so they are scalars. So it is just a scalar multiplication. Okay, so same thing. Now there is one more property that I should mention: the positive definiteness. Okay, so vectors in C2 has they are it is positive magnitude. Okay, so what do I mean by that? So we have seen. So yeah. So what does magnitude means is basically the length of a vector. Okay. So similarly, for any vector, even if it is a vector in complex vector space, you can associate the concept of length to it. So this positive definiteness allow you to do that. So this positive definiteness allowed you to do that, and how do we see that? So it is if you take any vector in C2, their dot product, the complex dot product will lie inside R. Okay, this will always is true. This implies that u dot u, and moreover, this has to be a positive quantity, and this is a positive quantity. Okay, so just let's see an example. Let's take an example. So what is, or let's take the general case itself. So let's say you have u is equal to u1 u2. Okay, and you are doing the inner product of u with itself. So what will you get? You will get u1 bar plus u2 bar. Okay, now what is this u1 bar? This is nothing but the modulus of u. Okay, modulus of u1 bar. No, sorry, modulus of u1. This is modulus of u1 square, and this is modulus of u2 square. And this is a positive quantity, and this is also positive number. Now, now we can answer your question, Tanji. So you asked me earlier that why do we take u1 bar? Okay, so in order to satisfy this positive definite condition, we need to take conjugate of vectors of complex numbers. Okay, otherwise this positive definiteness will not make sense if you just take any random product. So that's why we need to have this human bar and u2 bar to define this positive definiteness. Okay, so these are the properties for C2. Now in case of R2, so let's do the R2 case. So what are the properties that we see? We have seen the conjugate symmetry for C2. For R2, the conjugate symmetry does not make sense, but the symmetry makes sense. Okay, so you can, it doesn't matter which vector you take first to do the dot product, that we have seen. This one here. For linearity, again, linearity will always make sense for dot product in R2. So let me just write down the expression. So A for U1, UV in R2, U1, U2, and V in R2, and A and B in R, A U1 plus B U2 dot product with V is equal to A U1V plus B U2V. Okay. Now, what about the conjugate linearity? So, because in real numbers there is no conjugate of a real number is itself. So we will have, and we have this symmetry in this case. So because of the symmetry and the linearity of the first coordinate, we also get the linearity in the second coordinate. Okay, so we do have linearity in the second coordinate. So and A and B in R we have linearity, so it is u a, just a minute, Sonal, a v1 plus b v2. This is equal to a u dot v1 plus b u dot v2. Okay, yeah. So yes, Sonali, what's your doubt?
So in first property, u dot v is equals to v dot u conjugates. So while doing the v dot u whole conjugates, we have to do the explicitly for y conjugate dot u conjugate, or just we calculate the v dot u and then we just conjugate that answer.
Either way you will get the same thing.
Okay, sir. So, what's the difference between the conjugate linearity in the second and the first argument? And could you please explain the again the in the second argument, because I
Yeah,
didn't
so
get it.
conjugate linearity is this expression. Okay, when you have uh, when you have a linear expression, when you have a linear expression in the second coordinate, okay, and you are doing the dot product, then it just a second. Have I made a mistake? Okay, just give me a moment.
Okay, sir.
No, this is fine. Yeah, so I made a mistake by writing this. There is no bar here. Uh, there is no bar here. Just need, as we noticed, there is no bar here also. Right. So yeah. So what was your question? Yeah. So in the conjugate linearity, we have a linear. We may have a we have a linear expression in the second coordinate, and while performing the dot product with the complex number, we get the complex number zi's comes out as the conjugate of that. So it's a linear expression, but we have the conjugates of zi's coming out, not the complex number itself. Whereas in the case of linearity, we should come up, the zi should come out. Okay, that's what happened if you have the linearity in the first coordinate. If you have linear expression in the first coordinate, that's what happens. So that's the difference between conjugate linearity and linearity. Is that clear?
In first, we just multiply the v in the right hand side, and in second argument we just multiply to the v u as in the right hand side, left hand side. So
Yeah.
there also
So
having some difference in this.
yes. So that's what I'm saying. This is the first from left hand side. This is the first component. Okay. So the first component is linear. When your first coordinate or first component or first argument is linear, okay, then you have linearity. But when the second argument, second component is linear, then you have conjugate linearity. That's what it is. Okay. Is it clear?
So here the z is not treated as a scalar; it is treated as the complex number, and when we do the conjugate of the z, we get the different value of the z.
We get the different value of the z.
Means conjugate of z.
A conjugate of z is a different complex number, right? Unless
Yes,
z
sir.
is a real number, uh, it's a different complex number.
Okay, sir.
Right. So it is positive definite in C2. Now let's see what is the in case of R2. If you have two vectors in R2, then what does this mean? So suppose you have if you have if you have a vector in R2. So let's say you think that you have a vector, let's say W, which is um, which is x comma y, and it is in R2. Okay, then what does positive definite means? Is that v dot v is should be should be positive. Okay. So what is v dot v? V dot v is nothing but x1. So you just use the definition of dot product in R2. It is first coordinate multiplied together plus the second coordinate. multiply together. So it is x square plus y square. And because it's a positive number and we are adding up two positive numbers, it will always be uh, positive or 0. So this is what the positive definite means in R2. Okay, this is what positive definite means in case of Z2. So this is positive definite in case of C2. Sorry, this is in C2. This is in R2. Okay. Now, once you have the notion of dot product, we can talk about the notion of distances between two vectors. So now let's see. So let us quickly recall a magnitude of a vector in V. So in R2, we have seen that whenever you have a vector, you have a direction. So vector means a direction and a magnitude attached to it. So similarly, if you have a vector in C2, then what is the magnitude of that vector and what is the direction of that vector? So direction we know. Now, what is the magnitude of this vector? For magnitude is always a real number. Okay, so for that, we the magnitude of a vector u in C2 is nothing but uh, the square root of u dot u. Okay, so this is the magnitude of the vector. So now let's compute a few. So what is the magnitude of 1 comma I? So it is square root of 1 dot, yeah, yeah. You anyone want to tell me what is the magnitude?
0.
0.
1 square by 1 square plus I square, so 0.
Right, right. Is it that? Let's see. So what is this dot product? Dot product is 1 times um, 1 times the conjugate of 1, which is again 1. Okay, so it is 1 times 1 plus I times the conjugate of I. Right, the second coordinate is I. So conjugate of I is minus I. So if you square it, so the second coordinate become minus I square. What is minus I square? It is minus 1. Right. Minus I square is plus 1. Sorry. So it is square root of 2. It is not 0. Okay. Only 0 comma 0 has uh, uh, magnitude to be 0. No other vector has magnitude 0.
And
Okay.
this is clearly working because of your positive definiteness property. Otherwise, it won't
Yes.
work at all.
Yeah. By the definition, we have defined complex inner product in such a way that it will always make sense. Now, let's look at example B. What is the
Also, one more thing.
Hmm.
This double bar notation, it's for when we are taking the magnitude of a vector.
Yes,
And the
yes.
single bar notation is the magnitude
Modulus.
of a
Modulus.
modulus.
Yes.
Okay.
So, yeah. So, what is the magnitude of the second vector? Anyone?
Is it root 14?
Root 14. Let's check. So, it is 3 plus 2i. So, it is basically 3 square plus 4 square. Plus minus I. So, it is minus 1 square, that is 1. And then square root of all. So, it will give you 9 plus 16, that's 25, 26.
That's 2 square, right? 3 square plus 2 square.
Right, 3 square plus 2 square. So then it should be 40. Yeah. Yeah, it's 40, square root 40. Okay. So now how do we define distance between two vectors in C2? Simple, the same way to define the distances we do in R2. So we consider the difference between these two vectors. So difference of these two vectors makes sense because it is a vector space. And then we take the magnitude of that difference vector. Okay, so this is the definition of the distance between two vectors in C2. Similarly, in R2, if you have, let's say, two vector V1, U1, and U2, we define the distance between U1 and U2 in the same way, or the magnitude of the vector in the same way. So then it will become my U minus V. What is U minus V? If I take my U to be x1, x2, and V to be uh, x1, y1, and uv to be x2, y2, then what is u minus v vector? U minus v is x1 minus x2, comma y1 minus y2. So the length of this vector will be the square root of x1 square plus x2 plus y1 minus y2 square. So in particular, length of a vector in R2, or magnitude of a vector in R2, is nothing but the dot product of vector with itself. Now what is that thing? That is nothing but x square plus y square. So this is in R2. So case in R2 is simpler than the case of C2. Okay.
Excuse me.
Yeah.
When we say distance, we are still just talking about the displacement between the arrowheads, right? The vectors go from origin to a certain
Yes.
point. That's why we call them position vectors. And this distance is just the displacement between them still. Is that still there?
Yes.
In complex, even in C2, it's very difficult to imagine anything because it's two planes intersecting with each other. Could you paint some picture of the distance if possible?
For C2, it will be difficult because it is because I cannot draw C2. First of all, it's a four-dimensional real vector space or two-dimensional complex vector space. So, but you can have a schematic diagram which can help you visualize. But the schematic diagram will be the same as the diagram I will draw for R2. So let's say you have complex lines as your axis. So this is your complex CX and complex. So this is complex Y axis. This is complex X axis. So what do I mean by that? It means simply that any point in this is of type A plus IB type, and similarly any point on Y axis is also like that, X plus I Y type. And when you take any point in between, so you can think of that it is Z comma 0 type, and here any point is 0 comma Z type. Okay. Z1 or Z2, let's say. Okay. So now in this, the distance is precisely, suppose you have a vector like this, and suppose you have another vector like this, then the distance is precisely the distance between these 2 points. And what is that distance? That distance is nothing but the distance between the arrowheads, or the length of this vector. What is the magnitude of this vector? So first we need to find out what is this vector. So if this is vector u bar, this is vector v bar, then what is this vector? This vector is precisely u minus v. Okay, because if you add this vector, you will get v vector back. So this vector is pointing towards like this. Okay. So magnitude of this vector will give you the length. Will give you the so length of this vector or magnitude of this vector is equal to the distance between the arrowheads or the points which u vector and v vector represents in C2. So it's the same logic that you have in the case of R. There is no difference. Similarly, you can also talk about the angle between two vectors, even in C2 also. Okay. So let's first recall what is the angle between two vectors in R2. Suppose you have two vectors in R2, u and v. The angle between them, that means the cost value of that angle is u dot b divided by the length of u times length of v. Okay. So for example, if you have these two vectors 1 1 1 0, then what is cos theta? Cos theta is precisely 1 1 dot 1 0 divided by the norm of 1 1 and norm of 1 0. So what is this dot product? Dot product is 1 divided by square root of 2 times 1. It is 1 by square root of 2. So which value of cos theta? So which value of theta, for which value of theta? Cos theta is equal to 1 by root 2. It is 45 degrees. So this angle should be 45 degrees. So theta should be pi by 4. Okay. So I'm looking at the least degree, least angle possible. Okay. You can have the periodicity. You have the cos functions and periodic functions. So if you add them up by 2 pi, you will get the same vector. But I'm not doing that. In case of complex number, we need to have a real number on top of it. Okay, that numerator is a real number. But in case of complex number, if you do the complex inner product, you get a complex number as output. So you need to take the real part of that complex number, and then you have the same formulation. You divide by their magnitude. Magnitude are always real number, so this makes sense. So this distance will be that. So this will be your angle. So now what is cos theta for this example? So I dot I comma minus I dot with 1 comma I divided by the magnitude of u. What is magnitude of u? It is 1 square plus 1 square, which is square root of 2. What is magnitude of v? It is 1 plus 1 square. It is square root of 2 again. So then it will be 2. And what is the dot product? Dot product is 1 dot 1. Sorry, I dot 1 is will give you I. You know, take the real part of it. Okay. So real part of 1 comma, sorry, 1, sorry, I, and then minus I. So we will get minus I times minus I will give you plus 1. So it is 1 plus I. So what is the real part of that? Divided by 2. Real part of this number is 1. It is 1
It
plus 2.
would be minus 1, right? Because it would be minus I conjugate of I. So conjugate of I would be minus I. So that will become
Yes,
plus
yes, yes.
I square. So it will
Yes,
be
yes.
minus 1.
Yes, so it is minus half. Now, what is this angle minus half? Cos theta equal to minus half. It is like 180 minus pi by 3, right? Pi by 2, pi by 6. 180 minus pi by 6. That means pi minus pi by 6, which is 5 pi by 6. Okay. So this will give you that theta is equal to 5 pi by 6.
Or sir, it can also be 3 pi by 4 also. Oh no, sorry.
3 pi by 4 is going to be
Yes,
0.
sir. Also, it would
1.
be 1 by root 2.
Yeah, and that will be 1 by root 2. Okay, so this is all good. Now, so we have a concept of perpendicular vectors in R2. Okay, so vectors are going to be perpendicular to each other, and uh, how do we formalize that concept of two perpendicular vectors in R2? We look at their dot product. Okay, if the dot product is 0, then they are perpendicular to each other. Okay, and that precisely comes from this formula. If you look at this formula so if you calculate this formula for cos 90, then this should be 1. Okay, so
So that
sorry,
should be 0.
that should be 0, right? So this implies that u dot v will be 0 if the angle between them is 90 degree. So we can generalize the same for C2 also. So in particular, we say two vectors u and v in F2, where F2 I mean that it could be C2 or R2. Okay. Two vectors in F2 are orthogonal if their dot product is zero. Okay. So you need to be careful because I am taking a general definitions, but you need to be careful when you have vectors in C2, you have a complex inner product applying. When you have vectors in R2, you are applying the dot product for real dot product or standard inner product of R2. So let's take this example. Are these two vectors, because these two vectors in R2, so I will be taking the inner product for R2. So what is this? What is the are these two vectors orthogonal to each other? So let's see. So it is 2 times 3 plus minus 3 times 2. So it is what? It is 0. Right. So they are perpendicular. So that means 2 comma 3 is perpendicular or orthogonal to 3 by 2. 3 comma 2. Now look at this example also. So are these two vectors orthogonal in C2? So again, this dot 1 1, if you multiply, you will get I minus I. So it is 0. So they are also orthogonal to each other in C2. Now, orthogonal vectors are linearly independent in nature. Okay, so how to see that? Because you can look at this picture itself and keep. Uh, so, for example, whenever you say two vectors are orthogonal, that means you have this picture like this. They are perpendicular to each other, and you can clearly see that when two vectors are linearly dependent to each other in a vector space of dimension 2, when they are multiple of each other. Clearly, these two vectors are not multiple to each other. Okay. So that means they are ortho. So whenever you have orthogonal vectors, they are always independent to each other. Okay. But two independent vectors may not be orthogonal to each other. Okay. That you can see from the second figure. So you have two independent vectors. So the vectors in second figures are independent. I'm talking about this thing. So vectors in second figures are independent. U and V, they are independent because they are not lying in the same direction, but they are not orthogonal because the angle between them is not zero, is not 90 degree. Okay. So how to check quickly that? You just look at their dot product. If the dot product is zero, then they are orthogonal, hence they are linearly independent. If their dot product is not zero, then they are not orthogonal, but they can still be linearly independent. Okay, so let's take an example of two linearly independent vectors. So for example, 1 0, and so let's take these two vectors only. So what is this vector? This is 1 1. Okay, and this is vector, this is 1, this is 0 1, 0 1. Okay, so clearly these two vectors are independent to each other, but their dot product is not 0. And in this case, I am taking 1 1 and 1 minus 1 1. Right? Clearly, these two vectors are independent also, and they are orthogonal also. So orthogonality always implies in independence. All right. Now, now you can have a set of vectors in a subset of vectors in your complex vector space C2. Now you can ask when two vectors are orthogonal to each other. Okay. Or in particular, given a subset, whether a subset is the set of all set of given a subset of vectors, does every vector in the subset is mutually orthogonal? What do we mean by that? So suppose you have v1, v2, v3. So this is a set of vectors in S. set of vectors S in, let's say, C2. So they are said to be orthogonal to each other. Let's say two vectors. So they are going to be orthogonal to each other if V1 is perpendicular to V2. Okay. Or the dot product, let's write dot product is equal to 0. So such set is called the orthogonal sets. Okay. Now you can have orthogonal sets become basis of C2. Okay. Because we already know that orthogonals are independent, linearly independent. And if they are two in number, then they will span the whole vector space. Okay, that means C2. So you just need to know if you have two orthogonal vectors in C2, then they will always be the orthogonal basis. Okay. So, so two orthogonal vectors in C2 form a basis, form an orthogonal basis of C2. Alright. For an example, 1, 0 and 0, comma 1. Okay, this is one set of example. Okay. Now, what is orthonormal? What does orthonormal mean? So orthonormal means, so let me just paste it on top. Okay, what does orthonormal means? Orthonormal means that each vector in the orthogonal basis has magnitude equal to 1. Okay. Each vector in orthogonal basis has magnitude equal to 1. Okay. For example, look at this example. Look at this example. So they are clearly the basis. So first we need to check, for in order to check the basis, we just need to check whether they are orthogonal or not. So they are clearly orthogonal. So they are basis. But are they orthonormal also? That means the norm of each of the vector is 1 or not. So let's look at that. So it is 1. So norm of the first vector, or the magnitude of the first vector, is 1 by square root of 2 plus 1 by square root of 2 square root of this. Then you will get 1 by 2 plus 1 by 2, which is equal to 1. Similarly, for the second also, you can do the same computation. Okay. So it is an orthonormal basis of C2 as well as of R2 also, because these two vector lies in R2 as well. So they are orthonormal basis of C2 or R2, or both of them, they will be the orthonormal basis. Now, once you have an orthonormal basis, so there is a easy way to find out the coordinate presentation of any vector with respect to that orthonormal basis. Okay. So suppose, for an example, you want to find out the coordinate representation of 1, comma 2 with respect to these orthonormal bases. Okay. These orthonormal bases. So how will you do that? So the easiest way is to take dot product of the vector V with your basis vectors. So A is nothing but, so look at this. If you dot product V with U1, okay, what will you get? You will get A U1 dot U1. So first let me write it down. So what is V? V is U A U1 B U2. Okay, dot U1. Now it has symmetry in the first coordinate. Both of the inner product has symmetry in the first coordinate. So what it will be? It will be u a u dot u1 plus b u2 dot u1. Now, what is the first quantity? u1 dot u1. u1 dot u1 is the magnitude of u1, right? So u1 dot u1 is the magnitude of u1 square. Okay. What is u2 dot u1? u2 dot u1 is 0 because u1 and u2 are orthogonal to each other. So it is 0. So we will get a and times u1 square, normal magnitude of u1 square. Now what is magnitude of u1? Because it is an orthogonal basis, magnitude of u1 is 1. So it is just a. So a is v dot u1. Okay, and similarly b is v dot u2. So finding coordinates with respect to an orthogonal basis is easy. You just take the dot product with the each of the orthogonal basis vector, and then you will get the coordinates with respect to that vector. Okay. So in this case, what is a? 3 by root 2. And what is b? It is minus 1 by root 2. Okay. So this is your answer. Okay. So orthogonal complement or a dual. So we have noticed that when you have a vector space C2 or R2, there are vectors which can be orthogonal to a given vector. Okay. And there will always be one vector at least which is orthogonal to some vector. Yeah, Tanjit, do you have anything to ask?
Just the previous page. Sorry, could you scroll up?
Yeah.
We did v dot u1. We did for u1, and then we didn't do both coordinates of u1. I feel.
Similarly, you can do that for U2 also. That's what I'm
No,
saying.
no, but the u1 itself has two coordinates. So I think we didn't do it for the second coordinate, or have we done
Yeah,
it?
yeah,
And
because
I'm
it
not
is 0.
sure.
That's what I'm saying. This is 0. They are orthogonal to each other. U1 and U2 are orthogonal to each other, so it is 0.
But the way I was looking at it is AU1 plus BU2 has two coordinates in it, correct? No?
Yeah,
AU1 plus BU2 has two coordinates, and
right.
the top coordinate actually goes with all the first coordinates of U1 and U2, and then that we take with the first coordinate of U1 itself. But for the entire thing to go to
No,
0,
we are
we have
using
to.
linearity. Look at this. We are using linearity in the first argument. Okay. So if you use linearity, it will expand into this. That's the linearity of dot product. And then what is the first number? This is u1 dot u1, which is the magnitude, square of magnitude of u1. What is the second quantity? Is u2 times u1, u2 dot u1. So that means, but u2 and u1 are orthogonal, so it is 0. So you don't need to go into that detail.
Uh, can you say that again, please?
I'm using linearity in this. So this is the first argument has a linear expression. I'm using linearity to expand this and write the left hand side, the right hand side. And now this quantity u2 dot u1 is 0 because u2 is orthogonal to u1. The first quantity becomes the magnitude of u1 square. And we know that because it is an orthonormal basis, magnitude of u1 is 1. So this becomes 1. This is 0. So it is A. That's your answer.
So A in our current example is just uh, 1, is it? The first coordinate of V. Is that what A is here?
No, no. A is v dot u1. Now, what is v dot u1? V dot u1, you do the, now you need to do the computation here. I haven't done the computation. I've proved that the first coordinate is going to be v dot u1, dot product of u1 with v. Second coordinate is going to be, not coordinate, second coefficient is going to be a dot product of v with u2. Now you do the computation. What is v dot u1? That will
So
turn out to
this
be,
is for finding out V dot u1, and then we find out V dot u2, and we get two numbers, and those are actually the coordinates of V in the orthonormal basis. Is this how it is?
yes, yes.
Okay. Okay. Thank you.
Now, orthogonal complement or dual. So, the orthogonal complement of a vector v is noted by this symbol, and it is defined as set of all. It is defined as set of all vectors that are orthogonal to v. Okay, so this consists of all vectors that are orthogonal to v. In particular, this definition. Okay, this R2 need not to be R2. It can be C2 also. So let me write F2 here. Similarly, you can have a subspace of C2 or R2, call that to be S, and then you can define S perv. So this notation is called perv. Perv. S perv. So what is this S perv? S perv is set of all vectors U in F2 such that U dot V is U dot W is 0 for all W in S. That means it is set of all vectors in F2 which are perpendicular to your subspace S. Okay. So for an example, let's take an example to understand things more clearly. So let's say you have plane R2. Okay. Suppose you have this plane R2 and you have a line like this. So this is a line. Okay. Now what are the possible, what is S perv? S perv is precisely set of all vectors which are perpendicular to S. Okay, so this is my S. So what is the set of all perpendicular vectors? This is perpendicular. So this vector is perpendicular. Any vector in this direction is also perpendicular. Similarly, this vector is also perpendicular, and so on and so forth. But you may say that this vector is also perpendicular to this, to this vector. So my question would be, is it? Because if you look at, so what is this vector? This vector, you need to look at the position vector. So this vector is basically this vector, this point, but this is making an angle of theta with this point. Okay, so they are not perpendicular. So the only perpendicular vectors will be the ones which will make an angle 90 and passing through and starting at origin. Okay, anything which is not starting at origin will not be perpendicular to this subspace, will not lie in this subspace. Okay, so right, so what you will see that what do we notice here is that this line, which is this line, becomes, so this line, yeah, so this line becomes perpendicular to S. Okay, we call this line to be the S perp. So as you can see that line is perpendicular to S. So this line is also a subspace, okay, of R2. The same thing you can think of in your head for C2. Okay, so you can think that there is a one-dimensional subspace in C2 S, and you can have this S perp, which is all vectors are perpendicular to that. Same thing you can visualize in C2 also. So what you have noticed in this case is that uh, the subspaces, for a subspace, the S perp is also a subspace. Okay, uh, that's the first thing you have noticed. And if you have just one vector, which I have in the earlier case, if you have just one vector, let's take that case as well. Suppose you just have one vector, so that vector could be in any direction. Let's say this is your vector. Okay, so then what is the perpendicular vector to this? So anything that is like this. So how many perpendicular vectors it can have? It can have actually many perpendicular vectors. Okay, in particular infinitely many perpendicular vectors. So this looks like a perpendicular vector to me. Okay, and this is V, and this is V, and this is V per. Sorry, this will be an element in V per. Sorry, this is W in V per. Okay, but anything that is spanned by W will also be in V per. You need to notice that. Uh, so yeah. So that's the first thing that we have noticed, that S perp is also a subspace. Okay, you can also check this by using the property of a subspace. So for that, you need to say that if U V is in S perp, then U plus A V is also in S perp. So it is clear, because if you take, so what do you need to check for that? You need to prove that U plus AB. For that, you need to check U plus AV is in S perp. So for that, you need to say for W in S, we need to prove that uh, V dot U plus AV should be 0. Now what is this? Now you can use the linearity in the conjugate. So conjugate symmetry, conjugate linearity. Let's use conjugate linearity. You will get W dot V plus A bar W dot V. Now because U and V, now since U and V is in S perp, W dot W with U and W with V will be 0. So this implies that W dot U plus AV is also 0, because these two things are 0. So that means what? That means S perp is also a subspace. Okay, that we have seen in the example also here. All right.
So can you explain this once again, that how you got U plus AV? Like why did you wrote that?
Yeah, this is the condition for subspaces, right? Uh, if you want to prove a vector, a subset is a subspace, you need to check two conditions: whether it satisfies the addition, that it is closed under addition, or and it is closed under scalar multiplication, right? So that's what I'm doing by checking, by proving this. So or you
Okay,
can, yeah, you can take both things combined and then you can prove this. Now, second thing is that dimension of S plus dimension of S perp is 2. Now, why is that so? Because if you have S, let's say if S is a line, Okay, that means what? That means it is spanned by one vector, and S per will have another vector which is orthogonal to S. Okay, now you have two vectors which are orthogonal to each other, so they will span the whole vector space C square. All right, so their dimension will be equal to 2. Similarly, if your S is the whole plane, then S per will be zero vector. So then again it is satisfied. So you have three cases. So if S is a point, if S is origin, then S per is the whole C2 or R2. Okay. If S is a line or a span of a point or a span of a non-zero point, then S per is a perpendicular line. It is again a line. And if S is the whole plane, then S per is going to be the point. Right. In each cases, their dimension will be equal to 2. Okay.
Excuse me.
Yeah.
When we say dimension of C2, are we trying to
Yeah.
say 2 or 4?
2. Whenever we're talking about complex C2, that means we are looking at the complex dimension. The field is C. Field
So
is not
we
R.
are we are still talking about dimension 2, but in reality, if we try to build it up, we are unable to build it because it is going into the fourth dimension. By the time we make one complex plane and put another real line there, we are out of 3 dimensions. We don't know where to
The
put
point is
that.
because we're trying to build it with real axis. If we use complex axis, then you can think of it as like a complex plane inside. You can think inside you can think of a complex plane, but if you try to imagine complex plane in a real world, then you need 4 dimension. Okay, so there can be a world where you have complex as one of the dimension, some complex world where complex line becomes a one-dimensional thing. Okay, so then you can have complex plane there. But if you try to, because because we are living in a real world, so in real world we have 3 dimensions only, and in real world complex plane becomes a 4 dimensional thing with respect to real scalars. So yeah, so whatever you're saying is correct. Okay, so dual of a subspace is the subspace itself. So let's take an example. Let's take the previous example itself. So if you look at this dual, so you start with S, you look at the dual, it is this line S bar. And if you start with this S bar, what is the dual or orthogonal complement to this is S itself. Okay. So let me repeat it once again. You start with S. Let me take this figure downstairs. So you have this. So you start with S. Okay. You look at this dual or orthogonal complement. You get S per. Now, if you look at the orthogonal, if you take the orthogonal complement of this S per, you will get this S, right? So what is happening is S per of S per is S, or of S dual of S is S itself. That is what is happening. Okay. Now, uh, so this inner product that we have seen defines a linear map also on your vector space C2. So in particular, I will be taking F2, and I will be taking the inner product of complex numbers, complex planes, complex inner product of complex plane. Okay. So let's take F2 can be C2 or R2. Okay. So That should be clear by now. You just need to, if you have complex vectors, that means you are working with complex uh, inner product. If you have real vectors, then you are working with a real inner product. All right. So let's say you have defined a linear map from F2 to F2 as this. You have fixed a vector V in F2, and with respect to the canonical basis, it has coordinates V1 and V2. Okay. So you can define a map from F2 to F2 by taking a vector. How does it define? You take a vector V1, V2, U1, U2, and map it to the no, this is uh, yeah, this is not a linear map from F2 to F2. Just give me a second. Yeah. So it's a linear map from F2 to F, right? It's a linear map from F2 to F. Okay. So how does it define? It is defined. You take a vector in F2 and you perform the dot product and you get this. So it is now let's see whether it is a linear map or not. It becomes a linear map because of the first condition. Okay, so let me rephrase the definition. The definition is so you define a linear map like this. So you take a vector u, okay, and you take a map vector u which is u1 comma u2, and you map u1 comma u2 by v into this u dot v, okay, which is nothing but u1 b1 bar plus u2 b2 bar. Okay. Now, because u1 is in the first, u1 is at the first place, u is the first argument. We have linearity in the first argument, so it becomes linear uh, map. It's for linear map. What do we need to prove? We need to prove TV of ZU1 plus Z1 U1 plus Z2 U2 should be equal to T. Z1 must come out U1 Z2 T V U2. Okay. So now what is this case? So in this case, we have Z1. What is TV U1? Right. So now does this thing holds true? So just look at this definition. So what is the right hand side? Let me start with the left hand side. Left hand side is Z1 this is equal to Z1 U1 plus Z2 U2 dot product with V. Now use the linearity of the inner product. So you'll get Z1 U1 dot V plus Z2 U2 dot V. Now what is this? This is nothing but, now again we can rephrase this in terms of the linear map notation. Z1 TV U1 plus Z2 TV U2. Okay. All right. So this is a linear map.
Excuse me.
Yes.
I couldn't understand the definition. Sorry. We have
Okay.
written TV of u1 comma u2.
Hmm.
U1 comma u2 is one vector or two?
It is one.
If it is f2 to f, then u1 is one vector and u2 is another vector. Is that right?
No, it is one vector only. U1, U2 are the coordinates of the vector
U1, u2 are the coordinates.
with respect to
Uh,
some canonical basis. Hmm.
okay. So u1 is one coordinate, it is one complex number. U2 is another coordinate, it is another complex number. And then we are multiplying it with v. Why exactly that?
This is a definition. We're defining a linear map from C2 to C.
But v is having two components, as in v has two vectors, correct? No, v itself has two vectors. One vector is v1 and the other vector is
No, those are
v2.
not vectors. Those are. No, you are getting confused. Those are not vectors. These are not vectors. These are coordinates. V1, V2 are coordinates. So we fix a vector V in F2, which has coordinate presentation V1, V2 in uh, in with respect to some canonical basis. Okay. Then we define a map from. Okay, let's take C2 only so that it will be easier. I think this F is confusing. Okay, so you take a vector in C2. So what is a vector in C2? It has it is a two component vector. Each component is a complex number. Okay, so you take that vector, you fix that vector, and now you define a map from C2 to C. How do you define a map? So you define a map like this. TV of U is defined like this using the inner product of U and V.
So TV is taking us from a vector to a single complex number.
Yes, yes.
Okay, seems like I'm somewhat in the right direction. And in the linear map, then we are again looking at TV, which is supposed to take us from a vector to a complex number. Then the
Yes.
argument for TV on the LHS, uh, how can we think of it, please?
So, what is a linear map? Linear map is you take z plus u1. Okay, I got the confusion. Okay, so you are getting confused because I use the same notation here. Okay, so that is bad choice of notation. I understand why are you getting confused. So let me take a different notation. Hmm. Let's take a different notation of vectors. Let's take u and w. Okay, u and w. Okay, now you go through this argument once again. Now is it fine?
Okay, could you please walk me through this?
Yeah. So you are proving the linearity you are proving that whether this function is a linear map or not. So how do you prove that? We start with a linear combination. So that's the linear combination that I've started. Two vectors multiplied with the scalar, and then you're taking the sum of that. Okay. And then you need to prove that it behaves well. The scalar comes out, and you can write it as the sum of the the function acting on the vector only. Okay, that's the definition of linear map, right? So is this line clear to you?
That is the way we used to talk of linear transformation
Yes.
in R2 vectors, and that's how we used to write it. Only difference here is that in our R2 linear map, the dimension would not change. Here, the dimension has actually reduced.
Yes. 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 Okay. So now this is the definition for linear map, right? Linear transformation. This is the definition. You need to prove this. So we start with the left hand side, and I want to arrive to the right hand side. Okay. So you start with the left hand side. Left hand side is this. Now what is this? So we use the definition of this linear map. So this is the definition of the linear. Okay. Now what is this? This is dot product with first argument being a linear expression. Now use the linearity of the first argument of this dot product. So you will get this expression. So this is equal to this, right? And now what is this expression? Now each of this expression in this line can be think of it as U applied on TV applied on U, and the second is TV applied on W. That's all. Which is the right hand side of the expression.
And here, TV itself is just the inner product of the
Yes.
argument placed first.
Yeah, but TV is important because there is only one variable. U is the variable. The V is fixed. That's why TV. So the linear map depends on V because V is fixed, but U is varying. Okay. All right. So now let's look at this example. So let's define TV for vector 1 comma 2. So what is TV for vector 1 comma 2? Okay, let's take a vector which is some complex so that it will be, let's take this 2 plus 3i comma 5i. Okay, now what is this? TV xy. So TV xy. What is this? This is xy xy dot with v. So it is. So look at this definition. This is the definition. This is the dot product only. So x times 2 plus 3i conjugate y times 5i conjugate of this. So you will get 2x minus 3xi minus 5yi. Okay. Which is equal to 2x minus 3x plus 5 by whole thing in bracket times I. So this is your map. Okay. All right. Now we have seen that how to we can represent any linear map by a matrix transformation. Okay. Sorry, any linear map by a matrix representation. Okay. For that, we need to fix a basis. Once we fix a basis, we can write down a linear transformation with respect to the that basis and express it in terms of a matrix. So same we can do in this case as well. So if I take a canonical basis, orthonormal basis, or canonical basis E1, E2 for my vector space C. So let's take Okay. So now let's take. So you have. So your V is fixed. For a fixed B in C2, we have TV from C2 to C. So the matrix corresponding to TV is basically the first column is the image. So let me write it down. So first we start with the image of each TI, E1 and E2 with respect to the basis on the codomain. Now, what is the codomain? Codomain is C. So what is the basis of codomain? We will take basis to be just 1. This is your basis, singleton 1. So this with respect to the basis of codomain. So that means any coefficient Z1 times 1, Z2 times 1. So this is the image. So you can express T1 with respect to the basis of codomain. And now with this, we can write down the matrix by writing each of the. So this is TB of E1, TB of E2. So TB of E1 will be my first column, TB of E2 will be my second column. In particular, what is TB of E1? It is Z1 and it is Z2. So these are my coordinates. So this is the matrix representation. Now we can actually figure out what is this Z1 and Z2. How? We just need to multiply V with this. So what is V? So our V, I can again express my V with respect to E1, E2, right? So let's say V is equal to V1, E1 plus V2, E2. Let. Then, uh, yes, then what is TE1? TE1 is V dot, sorry, E1 dot V, which is E1. Now, what is E1? E1 is 1 comma 0. What is the coordinates of E1? 1 comma 0, right? So it is 1 comma 0 dot V1. What is V1? Yes. What is V? V is, what is V? Right. So what is V? V is V1 bar. Sorry. V1 is V1 comma V2. Right. So what will you get? You will get 1 times V1 bar uh, and 0 times V2 bar. So this is what V1 is. V1 is V1 bar. So Z1 is nothing but V1 bar. Similarly, Z2 you will get V2 bar. Okay. So this is how you can express your the matrix presentation of this.
Excuse me.
Yeah.
There is some difference in the way we wrote TVE1 above and TVE1 below. I'm having trouble with that, sorry.
Okay.
So in the upper part we wrote TVE1 is Z1.1. That's on the
Right.
codomain side.
Yeah.
The reason we took 1 was because it's one-dimensional on the codomain side.
Right. Right. Right.
But why 1? Why not just call it some complex number Z?
No, no. That is a complex number. One is a complex number, right?
1 implies a complex number.
What do you mean by one implies a complex number?
I mean, what is inside that one? It's supposed to be, as far as I see, a complex number, right? How are we um, um, resolving it into its components? Like complex numbers are a plus ib. So if we write 1 in place of that, what exactly is contained in that one, please?
So it is A is 1 and B is 0 in your expression.
So it's a complex number with no complex component.
No imaginary part, yes.
So that is just the real axis one then, in that sense.
It's not the real axis one. Look, when you have a complex, when you have a complex line, so when you say this is a complex field, so what does it mean? Is that you will multiply any complex number to it. So if you multiply one with any complex number, you will get that complex number, right? For what is in case of R also, you multiply any real number with one, and you will get that real number, right? So similarly, in complex also, you can express any complex number as z times 1, right? So what I'm saying is, look at this. So what I'm saying is that you have a complex line. So this is a complex line. Okay, when I say a complex line, that means what? That means it is set of all points z in C. Okay. So now you can write any point z in C as z times 1. Okay. Z is equal to z times 1, which is same as saying that z lies in the span of 1. Now when I say span, so I need to know what is my scalar field. In this case, the scalar field is C, not R. Okay. So scalar field is C. My scalar field is C. So what do I mean by that? Is that C is a one dimensional vector space one dimensional complex vector space one dimensional complex vector space. When I say complex vector space, that means my scalars are coming from complex numbers. Okay, that means you can think of any complex line as a span of 1 because my scalars are complex numbers.
But then again, for me, the question of what is one in the complex space remains. Is one
1 is
referring to
1.
the unit
1
circle?
is 1.
Is one
1 is 1.
referring
No,
to?
no, no, no. It's not nothing. It's just 1 as a real number. That is 1. That 1.
So 1 is equal to z is equal to a is equal to 1 plus bi, where b is equal to 0.
Yes. So you can write any complex number like this. Any complex number lies in the span of 1. You need to get comfortable with this idea. What do we mean by the span with respect to what field? That field is your Z, C. The field is your C.
Okay, thank you. I'll spend more time thinking about
Yeah,
it.
yeah. So I would suggest all of you to go back and have a look at complex vector spaces. Okay, the definition, do some examples of complex vector spaces, solve some exercises. Okay, I think it is covered in the very first week. So please go back there, go back to those lectures, go back to those notes, and try to recall all these things. Okay, and then we can have our discussion on Friday. from this point onwards. Okay, so I will today we have okay, so today we stop at this point, and I hope I expect all of you to revise this complex vector space concept, and if you have any doubt, uh, then also after revising, then we can discuss it on Friday. All right. Yeah, just get comfortable with this idea of complex vector
So
space.
can we think that earlier thing as z dot e1, then it would be z1 z2 dot 1 comma 0. So then we will get z1 into 1, because if we take the conjugate of 1 we will get 1, and conjugate of 0 would be 0. There where you wrote z1 into 1, there we can take it like z
No,
multiplying
but this is inside C, right? So what is the dot product of two complex numbers? There is no dot product. It is scalar multiplication only, right?
Yes, sir.
Think of it as in R. So in R, when you take two real numbers, what is the dot product of two real numbers? It is the scalar multiplication. You are multiplying anything with R. So, right. So it is a property of a field. So you need to recall what is a scalar field, what is a real field, what is a complex field. Okay. So any
Okay,
real number is inside is a complex number. Any real number is a complex number. Okay. So you can express any complex number as z times as some complex multiple of 1. That is easy to see, right? You can think of any uh, real number, any complex number as z times that same complex number times 1. Okay.
okay, got it.
Yeah. All right, everyone. Thanks for joining. So I stopped today's discussion at this point, and we hope to meet on Friday again. Okay. Bye.
Thank you, sir.
Yeah.